How do you think Google Maps find the shortest distance from our source to the destination? It uses some search algorithm like the best first search algorithm to find the shortest distance from the source to the destination. We can look more into the best first search algorithm. Best first search algorithm uses evaluation function to decide which adjacent node is most promising to explore. The best first search algorithm is a heuristic search algorithm used in various domains, including the artificial intelligence, graph theory, and optimization problems. It is similar to the Dijkstra's algorithm. It uses a heuristic function to guide its search. It is a informed search or directed search. It uses the it is like more than like the greedy search algorithm. It find the shortest path next to it. Priority queue is used to store the cost of nodes. We start the traversal from the initial node I. We have three options from initial node I, which is A, B, and C respectively. From A to the final node F, the heuristic value is 53. From B to F, it is 40, and C to F, it is 42. It is given. Now, next we need to choose which node we are going to next. In order to that, we have already told that there are two priority queues, which is open priority queue and closed priority queue. In open priority queue, we store the nodes which we are going to traverse, or options there nodes that are possible to be traversed. And next, the closed priority queue contains the nodes which is already traversed. In here, we know there are three nodes A, B, and C to be traversed. First, we push the initial node I to the open priority queue. So, after pushing I to the first open priority queue, we get A, B, and C as next node to be traversed. Then we transfer the node I to the closed priority queue after getting into it. Then we put A, B, and C in the open priority queue according to the ascending order. We have here B 40, C 42, and A 53 in open priority queue and I in closed priority queue. So we choose the next node according to the uh, lesser value. Here we have B, which is lesser to any else existing, which is 40. The C is, we know that is already greater than B, which is 42, and A is, A, you have a heuristic value of 53, which is higher than B. So we push the node B to the closed priority queue, and next node to be traversed are E and C. C we have already taken in last, and E is the new node coming forward, and A will be in the open queue. Only we need to add E to it. It will be in ascending. It will be ordered in ascending order, and next, and we will choose the lower value, the node containing lower heuristic value, which in this case is C. So we choose C to as the next node to be explored. So so we push so we put C in the closed priority queue, and we will have F and B in the open priority queue, which are the next node that can be gone to. With from F to F, we know that it is 0. The heuristic value would be 0 because F is the final node and F is the next node to be traversed. So we order it in ascending order, and we will have F as 0. So we will choose F as the next node to be traversed. So we will put F in the closed priority queue. So we will get the path such that first node will be I, next node will be B, then C, and final F. So as shown in the figure, we start from the initial node I, then go to second node B, then C and F. Here we chooses the shortest path from I is B, then B to C and C to F. We take the smallest heuristic values, and we find a path from initial node I to final node F. There are many applications for the burst first search algorithm. Some of them are it is used in robotic path planning. It revolutionizes the navigation of robot in complex environments, and also it is used in artificial intelligence, including the gameplay. The game playing algorithm uses first search algorithm to enhance game playing agents' ability to make strategic decisions and find optimal moves in the games. And and it is most used in data mining and pattern discoveries. The first search algorithm aids in uncovering hidden pattern and association in large datasets. Next, we can go to the next topic, admissibility. A heuristic function is said to be admissible if it never overestimates the cost of reaching the goal node from any node. It is also called an optimistic because it assumes the best possible outcome each steps, as like we have seen in our example. It chooses the next node by calculating the heuristic value. It takes the lowest heuristic value. The first algorithm that uses an admissible heuristic is guaranteed to find an optimal solution if one exists, because it will never pull a node that leads to the goal node with a lower cost than the current best solution. It is also important to note that a search algorithm is admissible only if and only if for any graph it always terminates. And the next topic is about monotonicity. What is monotonicity? Let's say a heuristic function is monotonic if it satisfies the condition, that is, for any two nodes n and m, where m is the successor of n, as we have seen in the previous example that we have initial node I and the other nodes A, B, and C. A, B, and C are the successors of M. of the initial node I. So the initial node I and the successor node A, B, and C, the estimated cost of reaching the goal node from N is not greater than the step cost of getting to M plus the estimated cost of reaching the goal node from M. And next, the monotonic heuristic is also called consistent because it ensures that the cost of reaching the goal node from any node does not decrease as search progresses. The burst first search algorithm that uses a monotonic heuristic can be more efficient. The burst first search is already efficient and it will be monotonic. It uses a monotonic heuristic function will be more efficient because it does not need to re-expand a node that has already been visited. Since the first time it visits a node, it finds the shortest path to that node, as we have seen in the example. And last topic is informedness. A heuristic function is informed if it provides more information about the cost of reaching the goal node from the any node than the trivial heuristic function. As we have seen the example, we got the cost of reaching from the every node to the final node. It is already given, so it is a informed heuristic function. The more informed a heuristic function is, the more it can reduce the size of search space and the number of nodes that need to be expanded. The informedness of a heuristic function can be measured by comparing it with the other heuristic function or with the optimal cost function. That's all about my topic. Thank you.